FAQ number 3. Okay, so trophy body diagram. Well, we have the F force. We have the the FK going against it. We have F of G, and we have Fn. Four forces. That's it. So F of N and F of G are equal. F of K is load less than the magnitude of F here, or the X component rather. So we can draw it a little more this way. And yeah, that should be good. So B, vertical axis. Well, if you're gonna graph it, the vertical axis would be the X, right? But since it's acceleration, we're trying to find acceleration, we have, and it's giving X of t and t. We set up the displacement function, or the position function. And since it starts from rest, there's gonna be no VI. So if we move it over, we're gonna have 2x, and t is gonna be on the bottom, so t squared equals a. And it's gonna be rise over run, so the rise is the 2x. So your vertical axis is gonna be the 2x. Horizontal axis, that's the t squared. So yeah, t squared and x squared, or 2x. So that's gonna be meters, and this is gonna be seconds squared, and that'll be the A of t graph. So we can plot the points here. We're gonna complete the table first. So we can just this is gonna be 2x, and this is gonna be t squared with the units of meters and seconds squared. And since this is x, we just have to multiply by 2. So if we do that, we can fill out the chart. So 72 meters, 0.072. And I already punched in all the numbers, and this is going to be all the values here. So just copy it all down. And the time is going to be squared. So you square this number. And that's going to be all the numbers. So now we're going to have to graph those points. The scale, we're going to make it into, to completely fill out the graph, we have 2 here, 2 seconds, and I'm going to divide evenly, so that this is 0. And then for the x-axis, I'm going to have 3 meters as the max. 2 again, because it'll round down. I round time up. Because round this up, round this down. So it'll be approximately. And we can divide up all these. As well as all these. And then we're gonna take the plot all the points. So it'll be approximately here-ish somewhere. Got somewhere over here. Another point's gonna be somewhere right here. And right here. Then those are 4, and then the last one is just 169. So a little bit right here, a bit over. And then we can draw the line that best represents it. That'll be the line. And yeah. Seconds, yep. And this line shows the average A of t. So using a straight line, calculate the experimental value. So the experimental value, it would just be the 3 point, take the first or the last 2 and then minus by the first 2. You get 3.042 minus 0.072 over 1.69 minus 0.04. That's going to be about 1.8 meters per second squared. The positive direction, line of motion. And we can use that. And the next question is going to be derive an expression for coefficient kinetic friction in those terms. So we can just go ahead and do the function f equals max. Set up the x and the y's. So first f in the y direction is going to be 0. And then fx has fk, since this would be theta, right? Or yeah, this here, theta here. So have the component minus the f of k. And yeah, that's going to be in the x direction. The y direction, we're going to have Fn equals to Fg. So it's the two forces are Fn minus Fg equals 0. So we just that. Yeah. Oh, forgot about the applied force for the y direction. We have this component right here. So Fn is actually going to be equal to Fg, which can be written as mg plus the f sine of theta, this component. And then we can just define what mu is. We take f k, we write it as fn, mu fn. And factor the or we can just isolate fk here instead. And we already have fn, and since mu is just fk over fn, just put this whole thing over this, have mg plus f sine theta, or it's the other way around, f cosine of theta minus ma over f sine of theta plus mg, and that's going to be equal to our mu. And yeah, that is the type question. So we get the E done. Now we do F here. Is applied powers, calculate the kinetic force friction of Fk. So we have Fk here, and we're given that we're given the force, theta, and the mass. So since the mass is 2, I believe, yeah, just plug in all we know for Fk. And since that force is 12 newtons, we have cosine of theta is 60 minus the mass times the acceleration. And this is where we have to use the experimental one right here. It's going to be 1.8. And when we plug all that in, we're going to have Fk is equal to 2.4, negative 2.4, because it's going this way. It's going against the line of motion, so take that as negative. That's going to be our Fk. And we can also do G, calculate the kinetic friction, or the mu, the coefficient of kinetic friction. So we just plug everything we know into this equation right here, because that's going to be F mu. So we're going to have 12 cosine 60 minus 2 times 1.8, which is just this thing, right? And then for the bottom, we're going to have 12 sine 60 plus mass times acceleration due to gravity. And when we plug that in, we should have a mu of about 0.08. So that's going to be our mu, K right there. And then we're going to move on to G, given, or we just did G, sorry. H, if the angle is decreased, what does it have on acceleration? Well, it's gonna increase, right? Because instead of it going down like this, when the angle is decreased, you're pushing more horizontally, right? So your horizontal is gonna be bigger than what it was before, and you're gonna have less force pushing in the y direction, making your Fn a little bit smaller, meaning your mu, or your Fk, sorry, it will also be smaller because your Fn is smaller, right? And yeah. So acceleration is going to increase. You're pushing more horizontally with less friction going against you. Because you're not pushing down, you're pushing sideways more. It makes sense. If you push the object down, you're going to have more friction than rather than just putting it sliding across, right? Let's guess the acceleration versus time graph. Well, acceleration, do it in a different color because it's going to be, right? So we can do it as 1.8 since that's our experimental value. Also our average, so we can do 0 time in seconds. And our acceleration in meters per second squared. And just gonna be a straight line across somewhere, right? Like, it could be anywhere really. But the value is 1.8 meters per second squared. Okay. And yeah, you need to draw anywhere. It doesn't really matter as long as you know the value of it. Moving on, a velocity graph. We're gonna be the time is gonna be t. This is gonna be v of t, which is gonna be in meters per second. Since there is acceleration and it's positive acceleration, it's gonna speed up, right? And velocity, since acceleration is constant, when you integrate a constant linear or horizontal line, you're gonna get a linear line, right? Increasing line. So linear like this. It's gonna start from 0, start at rest, and then it keeps going up by interval with the slope of 1.8, right? The slope is gonna be 1.8. So for every 1 second, it's gonna go up at 1.8. And yeah. And then we have sketch position time graph. Well, this is gonna be x of t, and this is gonna be our t. And we're gonna set this is gonna be meters. It's gonna be seconds. Since we have all our values here already, right? We can just plug them or graph them. Make it at slight interval 1.3. And we can decrease from there. Make it each an interval 0.26. And this is gonna go up to about 1.5. So then we can integrate so at interval 0.3. And when we graph it, it will be something like this. I'll go a little bit above because it is 1.52. And we're just graphing the regular ones, not the double or squared. Just the regular one that's given. And then when we connect it all, should be something like this. And this is gonna be just a regular number. This is gonna be something linear number, so like something t, right, times t, something times t, a times t maybe. And then this is gonna be t squared. And it'll be initial position and so on and so on. It's parabolic function, right? And yeah, that's gonna be most of the graph. And FRQ3.